So yesterday we finished talking about carboxylic acid derivatives. Today we're going to talk about acid halides and anhydrides. We know that acid halides are the most reactive carboxylic acid derivative, but let's talk a little bit about how we prepare them. So let's say we've got this carboxylic acid and we want to convert this into our acid chloride. Does anybody have a guess as to what reagent we would need to use? SOCl2. So you guys remember back to our chapter with alcohols, you can change an alcohol into a chloride by treating it with thionyl chloride. So we'll use SOCl2, and the byproduct of this reaction is going to be sulfur dioxide gas and HCl. There are a few other ways to produce acid chlorides. You can use PCl5, you can use oxalochloride, but the one that the Klein textbook primarily uses is SOCl2. So let's go through the mechanism. The mechanism is really similar to the mechanism we saw in our alcohol chapter. And the first step involves nucleophilic attack of our thionyl chloride. We said that thionyl chloride is a really, really good electrophile. So in this case, what ends up happening is the lone pairs from the oxygen on your carboxylic acid will actually donate down. You'll kick up electrons here, and then this carbonyl oxygen will attack the sulfur and kick up electrons onto the oxygen. I'll add in all of our lone pairs here, at least on our oxygens. What do you think the next step is going to be? Anybody have an educated guess? It's pretty similar to the mechanism from the alcohol chapter.
Add H or minus H?
That's a good idea, but let's see if we can get rid of a charge without doing a proton transfer. We've got a good leaving group. We've got chlorine there, right? Yeah, exactly. We can take the lone pairs from this oxygen, clamp down, and kick off a good leaving group. So that's the step before our proton transfer. At least that's how it's shown in most textbooks. Okay, and we've got Cl around. Quite often this reaction's run under basic conditions. So you'll use a non-nucleophilic base like pyridine. I'll just represent this base with B and a lone pair. This base will come grab this proton and we'll get our neutral molecule. So we've got our protonated base over here, and we still have that chloride floating around. If we look at it now, what we essentially have formed is an excellent leaving group. And we've got this nice dipole right here. So all we're going to do next is an elaborate nucleophilic acyl substitution, where chloride, in this case, is a decent enough nucleophile to actually attack in and kick up electrons. Okay, now we've got this good leaving group that we said was this guy. We can take these electrons from this oxygen, we can clamp down, and we can kick off this leaving group. Actually, I should show these as equilibrium arrows right now. And now we've formed our acid halide. Whoops, I made a mistake. There should be a sulfur in the center here. Let me clean that up. There we go. So now this is our good leaving group. And if we look at the leaving group that we kicked off, what's so special about it? Does anybody remember from our alcohol chapter? Yeah, bump down, kick off the chlorine. So if we do this, we actually end up forming sulfur dioxide gas, which bubbles out of solution, and then we reform another equivalent of chloride. So the thermodynamic driving force is actually the formation of the gas in this reaction, and that's what drives this out of equilibrium and allows you to isolate your final acid halide. Does that make sense? Does anybody have an idea for how to make an acid bromide? What reagent could we use for that? Yeah, PBr3. It's not as common. Acid bromides are quite unstable, very, very reactive. Acid chlorides tend to be a little bit more stable. Yep?
So this reaction, the entire reaction would not be in equilibrium, only the beginning half, or the beginning majority?
Yeah, I mean, if you're thinking about it as a net reaction, you would show it as a one-way arrow because you are driving it to the product side because you're bubbling off gas. However, if you think about the nucleophilic attacks, those could be reversible for the early steps.
So if the gas was left in there, would it, by any chance, like, go back to the other direction, but the chlorine and the SO2 react back and everything would react back?
It's pretty unlikely. The gas phase is just entropically a lot more favorable to form that gas and get it out of the solution. And so it's not going to really push back the other side very far. An analogy would be like dissolving CO2 in water. You do form a little bit of carbonic acid, but not very much. Yeah. Okay, so let's take a look at some reactions involving acid chlorides. There's one really easy reaction. And that is hydrolysis. We know hydrolysis just means you're going to break something with water. So let's think about what would happen if you reintroduced water to an acid halide. What do you think you would get out? Carboxylic acid. It's just the reverse reaction. You really don't go through the hassle of making an acid halide just to throw water back in because you'll just get your carboxylic acid back out. But you could, theoretically. The mechanism is pretty straightforward. We'll go through it really quickly. We've got this really good electrophile. Oops. We know water can be a decent nucleophile, so this will kick in. And then in the next step, chloride's a really good leaving group, so we can actually clamp down and kick off the chloride before anything else happens. And then, unless there's another base around, you can draw a chloride acting as a really weak base, in this case, to show formation of your final product and HCl. You like it? Yeah, it's pretty easy, pretty intuitive. However, it's not super practical. I don't know why you would bother creating an acid chloride just to hydrolyze it back to your carboxylic acid. One thing you'll often see with these reactions is if you are running them, you'll run them under slightly basic conditions in order to prevent formation of your really strong acid. So you oftentimes don't want to form a strong acid because it could do chemistry elsewhere in your molecule. So let's make a little note that often run with pyridine to avoid HCl formation. So instead of having chloride in this step act as your base, you would just have pyridine act as your base to deprotonate it. However, pyridine will also deprotonate your carboxylic acid. All right, let's take a look at another mechanism. This one's not going to be too earth-shattering. This is alcoholysis. Oops. So we've got our acid halide. This time we're going to use an alcohol instead of water. What functional group do you think we're going to get out? An ester, exactly. This is one reason why acid chlorides are so valuable, is they can really be used to make a wide variety of carboxylic acid derivatives. Also, these reactions, like I said, are often run in pyridine. And if you run this in pyridine, you'll also get a pyridinium salt out. But that avoids the formation of HCl and can actually facilitate the reaction. I'm not going to go through the mechanism, but the mechanism is completely analogous to the hydrolysis mechanism. Let's take a look at another one. What if we take an acid halide and we react it with an amine? What product will we get out? An amide, right? So you can also make amides really easily this way. However, if we want to get our neutral amide, we probably need to use some sort of base. Do we need to use pyridine in this case? What do you guys think? If you wanted, but the ammonia that you're using in the reaction is already a base, so why not just use extra ammonia? And that's exactly
what I said, if you want.
So in this case, what happens if we use excess ammonia? Well, then we get our neutral amide, and then we get ammonium chloride as our salt. So you don't need to use pyridine with these reactions. You can do analogous reactions with primary and secondary amines. Again, you would probably want to use excess so that you can isolate your neutral amide. Actually, let me change this to R prime. And you get your salt byproduct out of this. You can do this as well with secondary amines. However, the reaction gets a little bit more sluggish the bulkier your nucleophile is. There are better ways to form amides, and we'll actually talk about amide formation. I'm not sure if we'll have time this week. We may talk about it next week. All right. The other thing we can do with acid chlorides is we can reduce them. And we can actually reduce them a little bit more selectively than with the carboxylic acid. But let's do some review first. let's go over reduction chemistry. Let's say I want to go straight to a primary alcohol. What do you think a suitable reducing agent would be? Not PCC. PCC is an oxidant. Probably lithium aluminum hydride in this case, because if we think about this, this is pretty similar to a carboxylic acid. We probably want to overshoot it. We're not going to be able to efficiently stop at the aldehyde. So in this case, what you normally do is you run this using LAH, and then in step 2, what do we need? Probably water or some sort of weak acid. And just like with carboxylic acid reduction, we need excess LAH for this. So let's briefly look at the mechanism, and then I'll show you guys a cool trick with it. So we've got lithium aluminum hydride. The aluminum in this case is negative. One of these hydrides can attack in, kick up electrons onto that oxygen. We've got a really good leaving group, so we'll clamp down, kick off our chlorine. And we get an aldehyde intermediate. But as you guys saw with the carboxylic acid mechanism, it's really hard to stop at the aldehyde. So if you have any lithium aluminum hydride around, it will continue to reduce the aldehyde. Oops. So we'll have this hydride attack in. We've got our alkoxide now, and then we said in the last step, you usually need some sort of weak acid or water. So I'll just use weak acid in this case. You protonate this, and you get your primary alcohol. So let's make a little note. It is hard/impossible to stop at the aldehyde. Chemists weren't super happy with that as an outcome. So what do you think they tried to do in order to stop it at the aldehyde? You could control the temperature, yeah, so maybe try to freeze trap it. That gets tricky though. It might not work super well. What's another approach we could take?
So heat it in excess?
Yeah, you could try to control the equivalents and try to really hold it at one equivalent, but they found that they usually get mixtures out. Yeah, you could maybe control the number of hydrides on there. But let's think about lithium aluminum hydride's nice and small. Kind of has a free point of attack on any sort of carbonyl. What they did was they decided, well, what happens if we just bulk it up so that it has a really hard time attacking the aldehyde? And that's exactly what they did with this, and they found that it will react with the acyl halides, but not aldehydes. And they came up with this unique reagent. So bulky hydride source. Let's draw it out. And Greg was right. This one actually only has one hydride on it. We've got aluminum here. We've got lithium plus. This is called lithium. Oh, come on. tri-tert-butoxy aluminum hydride. It's so bulky, it won't react with aldehydes, but we know acid halides are quite reactive, so this will reduce an acid halide. Oftentimes, if you see this in the Klein textbook, he uses shorthand for it. He just abbreviates it LIALOR3H. Yeah, it's easier than drawing it out though, right? So if we look at this, let's take some examples. If we take an aldehyde, we get no reaction if we treat it with this hydride source. And the reason is, it is too bulky. However, if we take an acid halide, and we treat it with lithium tert-butoxy aluminum hydride, followed by a weak acid workup, we can actually stop at the aldehyde and we won't go, we won't go all the way to the primary alcohol. Let me clean this up, this looks sloppy. So this is a really nice way to make aldehydes. So you can imagine if you've got a carboxylic acid, you could say, well, we could reduce that carboxylic acid to the primary alcohol and then oxidize it up to the aldehyde. However, what reagent do we need to oxidize a primary alcohol to an aldehyde? PCC. PCC requires chromium. This doesn't require any chromium. So this can be a more environmentally friendly way to make an aldehyde, at least compared to PCC. All right. There's also some other cool reactions. Yep.
What does that say? Not
Observed. Sorry. My hand was getting tired. There are also a few other cool reactions we can do with acid halides that we can't do with aldehydes or ketones. So let's take a look at some of these. Reactions with organometallic reagents. What's a common organometallic reagent that we use to attack into ketones or aldehydes? Grignards. So let's think about what would happen if we threw a Grignard at this. And I'll just use a generic R prime MgX. What would we get out? Ketone. Exactly. However, this is really hard to control, just like with the reduction of the acid chloride. So if you have any more Grignard around in solution, what do you think you'd get out? Tertiary alcohol. So we'll do 1 and then 2. So let's make a note of this. Grignard reagents will add uncontrollably. it's really, really hard to stop at the ketone, and typically if you try, you get a poor yield. And so an alternate reagent was developed, and these are called dialkyl cuprates. And we'll talk about how these work. If you have an acid halide and you treat it with R2CuLi, this is our lithium dialkyl cuprate, you can actually stop at your ketone. So this is a pretty handy way of forming a new ketone. If you think about lithium dialkyl cuprate, let's draw what it looks like down here. You actually can view it more as two covalent bonds to copper. Copper does some pretty weird organometallic chemistry that we're not going to get into, but the important thing to remember is that lithium dialkyl cuprates will stop at the ketone and won't overadd. All right, so one thing I like to do at this point is to stop and create a reaction map, because we just covered a bunch of reactions. And so I'll get the skeleton formed, and I want you guys to help me fill in the reagents. And I'll put an ester up here. I'll put an amide over here.
Is the center going to be the chlorine?
Yeah, the center one's the acid halide. Oh, sorry. Thank you. I said ester, but I drew an acid. And then we've got our alcohol down here. We've got our aldehyde. Let's do this one down here. We've got our tertiary alcohol instead of primary alcohol. And then we've got our ketone. So in the center, we've got our acid halide, but we can interconvert between all of these different functional groups from an acid halide. So how can we go from a carboxylic acid to an acid halide? Socyl. Socyl 2. Thionyl chloride will get us there. You can also use PCl5 or oxalochloride, but this is the standard one from the Klein textbook. What if you want to go backwards? Agua. How about if we want to go from our acid halide to our ester? Yep, alcohol. And what else do we need? Pyridine. So ROH and pyridine. I'll just abbreviate pyridine PYR. And then what about for forming our amides? Yeah, NH3 for the first one. We need excess because it's acting as its as a nucleophile and a base. For this one, we would need RNH2 excess. For this one, we would need R2 NH and excess. And then what about to go to a primary alcohol? Yeah, lithium aluminum hydride. So we'll write LAH, and we need excess, followed by some sort of weak acid workup. And then what about for forming our aldehyde? Yeah, the bulky reducing agent. So we want to write LiAlOR3H. Sorry, it's getting a little cramped in here. H3O plus. That's so bulky it won't over-reduce it to the primary alcohol. And then if we want to add in 2 alkyl groups, Grignard. So oops, RMGX, and I'll write excess, followed by weak acid. And then for the ketone, lithium dialkyl cuprate, right? So R2CuLi. Take home message for synthesis problems. If you're ever in a pinch, acid halides are going to be your best friend. You can use these to interconvert between a wide variety of functional groups. They're the most useful intermediate for this chapter, and they open up the door towards all sorts of new chemistry. I did want to bring up a side note. This is relevant for the pod. We said that acid chlorides are more or less reactive than acid bromides. Yeah, a lot less reactive. And if we follow this trend, you can think about acid iodides, which are theoretical. However, they only exist for a fleeting moment. So I will say super unstable, moderately unstable, this one you can bottle, but needs to be in dry or cold environment. Why does it need to be in a dry environment? Yeah, it'll react with water. Acid chlorides in particular are known as lacrimators, so if they are introduced to the air or a humid environment, they'll actually cause your eyes to water because they're producing acid in the air, right? And that acid will irritate any sort of mucous membranes in your lungs or on your eyes. If you're interested in tear gas or chemical weapons, a lot of these involve alkylated compounds and are pretty nasty stuff. All right, let's stop and do a little bit of some synthesis practice. I think we're going to wait until tomorrow to get into our anhydrides. So for this synthesis problem, I'll give you 2 reagents, and I want you to figure out how to make our product. But before we begin, let's try to name our starting materials. What would the compound on the left be called? First thing we want to do is identify the carboxylic acid side of the molecule, right? So if we look at it, this would be our carboxylic acid portion. So let's go through and number it. We know it'd be 1, 2, 3, 4. So if it were a carboxylic acid, this would be 3-methyl butyric acid, right? But in this case, we've got a methyl group on the end, which means that its full name will be what? It would be methyl space 3-methyl butane O8. So we need that 8 suffix coming off at the end. Okay, so we're going to use this as a precursor. We're going to use benzene. And our goal is to make the following. So I'll let you guys work on this for a minute, but we need to figure out how to basically append that ester group onto the benzene ring. Oops, I forgot my L on methyl. Give you guys a hint too. You can work backwards on this, like any synthesis problem. So how can we get a ketone installed onto a benzene ring? Yeah, Friedel-Crafts acylation, but that requires an acid halide, right? So how can we go from our ester to our acid halide? Okay, so let's try to come up with a plan, and then we'll put it up on the board in a minute. But if you're getting stuck, try to work with your neighbor on this. Does anybody have a proposal that they want to share? Or do you guys need a little bit more time? Raise your hand if you need a couple more minutes. All right, I'll give you guys a little bit more time. All right, let's try to fill in the reagents we need for these reaction arrows. How can we go from an ester to a carboxylic acid? There's an easier way. Think about what nucleophile we would need to use in order to attack into that carbonyl. Water is actually not the greatest nucleophile. You could use water and a large amount of acid if you want, but what might be an easier route? Has anybody made soap? Sodium hydroxide. So we're going to cover this a little bit later this chapter, but if you use sodium hydroxide, right, the hydroxide can attack into the carbonyl, kick up electrons, and then clamp back down and kick off your leaving group. So first you treat it with hydroxide, then you can treat it with weak acid. That will convert your ester to your carboxylic acid. That's the greenest way. Alternatively, you could reduce it to the primary alcohol and then over-oxidize it back up with chromic acid. However, that's not very green. What do we need to go from our carboxylic acid to our acid halide? Acyl chloride? Thionyl chloride? All right, and then how do we do the last step? Well, first we need benzene, right? So you've got benzene and then aluminum trichloride, and that will do our Friedel-Crafts acylation. All right, I'll give you guys one last challenge before we leave. But I think you guys can do this now. Try not to cheat using the internet. It's too easy. I can't remember who I was talking to about this the other day, but does anybody know what this is called?
Caffeine.
Not caffeine. World's greatest painkiller for like sore muscles.
Ibuprofen.
Ibuprofen. So ibuprofen, you guys actually have enough chemistry knowledge to figure out a synthesis. So propose a synthesis from benzene and 4 carbon building blocks.
4 carbons with other functional groups? Or?
Sure. So I think I'll leave you guys with that challenge, but this is a really good practice problem. We'll talk about it when we come back into class tomorrow. Sound good? All right. If you guys need to get into lab to get any masses or melting points, try to come today because tomorrow I might be kind of busy after class.